This is Ken Willis at Cadence Design Systems. This demonstration will cover System SI's compliance kit for MIPI-M. The MIPI-M standard is targeted for short range, meaning less than 1 meter, mobile applications that require low pin count and low power consumption. The target bit error rate is 1e to the minus 10. This diagram shows a typical link configuration comprised of 3 lanes. The MIPI-M compliance kit built into System SI includes compliance checks for TX and RX eye quality, insertion and return losses, and jitter tolerance. We'll take a more detailed look at this in the demo. You can access the MIPI compliance kit from the top-level menu in System SI. From the MIPI compliance workflow, you can select from a number of templates. These are for pre- and post-route scenarios for both through-channel and crosstalk topologies. So we'll select one of these to start with. From here, it's as simple as following the workflow. The first step is to put in your channel models. This template comes with pre-configured models, so let's go take a look at those first. Here you can see our transmitter is configured for 5.8 gigabit per second data rate, a PRBS 9 stimulus pattern, and 8B10B encoding. If we take a look at the IBIS model assigned to this, you can see the pins on the device, the signals assigned to those pins, and also you can see a selection of multiple IBIS models that can go with those drivers. To view or edit the IBIS models, you can launch the IBIS editor. The package model used in this template is a 4-port S parameter, which you can see here. The main interconnect in this topology is a lossy coupled W element, which was created with our T-line editor. Here you can see the stack-up geometries as well as the trace geometries. The next step in the workflow is to set our AMI parameters, so we'll start with the transmitter. The algorithmic model that represents the transmitter equalization is comprised of 2 files, a DLL file and a .ami file. The .ami file defines the parameters that you can set. This parameter specifies a file where any tap coefficients that are automatically generated get written out to. This next parameter defines a scaling factor that allows you to easily scale the voltage swing of the transmitter up or down. The last parameter in this model is for the tap settings, which control the equalization strength. These include the MIPI-M presets of -3.5 and -6 dB of de-emphasis, plus a setting for nil, which you use if you want to use automated tap optimization. Now we'll take a look at the AMI parameters for the receiver. This consists of 2 modules, one for the CTE, or continuous time equalizer, and one for the CDR, or the clock and data recovery unit. The CTE comes with a couple of controls, one for the DC gain and one for the AC gain, as well as a capability to turn adaptation on or off. The CDR can also be turned on or off, but is generally just left on. The next step in the workflow is to select the actual compliance checks that you want to run, which brings up this page and shows you different categories of compliance checks. The first is the TX eye quality parameters. The next is the RX eye quality parameters that have to be met. Then you've got the insertion and return loss sections, as well as the jitter tolerance section at the bottom. In this case, we're just going to turn on all of the checks. The next step in the workflow is to actually kick off the checks. This will start to run time domain and frequency domain simulations. The simulation data will be collected and put into the report. When the simulation is complete, the compliance report is generated. Here we can scroll down to the first section, which is for the TX eye mask values. There are 3 criteria here that need to be met. One for eye height, one for eye width, and one for the eye mask. Clicking on the link in the report will bring up the eye mask plot, which clearly passes. Next, we'll look at the RX eye mask at the end of the channel. This has the same basic criteria as we looked at for the TX mask, but of course with different constraint values. Looking at the eye mask plot, we can see that this clearly passes as well. The next part of the report is to look at the differential insertion loss through the channel, which we can access by clicking on the plot in the table. This doesn't have a constraint value associated with it, but is provided for informational purposes. The next part of the report is for the return losses, which are plotted at both the TX and the RX. Reviewing the plots show that both of these are in good shape as they both stay out of the shaded region. The last result that we'll look at is for the jitter tolerance curve. This plot shows that the receiver is able to withstand significantly higher amplitudes of sinusoidal jitter than what it's required to. Note that the jitter tolerance curve doesn't intrude on the shaded region. When you're finished reviewing the results, you can save off a compliant sign-off report in HTML format. This provides a convenient way of documenting the compliance of your serial link. In summary, System SI comes with an automated MIPI compliance kit. This includes ready-to-run templates for pre- and post-route scenarios. You can include your own interconnect models and run them with the spec-level AMI models provided with the kit to check channel compliance, or you can include your own AMI models to check full link compliance. The kit provides push-button compliance testing to the MIPI M5 standard. For more information on System SI or any other Cadence products, please contact your local Cadence sales team or your Cadence channel partner in your region. You can also visit www.cadence.com. That concludes this demonstration. Thanks for watching.